Hi students, so I'm going to spend a little bit of time just looking at the data booklet with regard to the astrophysics section, just noting the important points. In the fundamental constants section, we have these two over here are important. Stefan Boltzmann's constant, this one here, and also the speed of light is obviously very important, 3 times 10 to the 8 meters per second. So those are the two that are really important there. Moving on, if I just go to the next page, we have all these multipliers which are also used a lot because distances and masses and so forth are often very big. We use these large multipliers over here, tera, giga, mega, and so forth. So you need to be able to work with these over here. They are important, the mega and so forth, and know what the value is for each of those. Going on to the next page, we have these conversions which we use a lot. So we have the light year, which is the light traveled in 1 year. The distance light travels in 1 year, and we know that's 3 times 10 to the 8 meters per second. So when we work it out, the number of seconds in a year, we get to this value over here. 1 parsec, which is another unit of distance that we define from the parallax method, is 3.26 light years. So if we multiply that by 9.46 times 10 to the 15, we get what that is, what a parsec is in meters. An astronomical unit, that is the distance from the Earth to the Sun, it is that many meters, 1.5 times 10 to the 11. So if we divide this value over here by 1.5 times 10 to the 11, we obviously get the number of astronomical units in a parsec. Okay, and then this 1 radian is equal to 180 divided by pi. We obviously use that with the parallax method because there it's measured in arc seconds. Arc second in radians is going to be pi is 180 degrees, so we divide it by 180. That will give us in radians 1 degree, and then you've got to divide by a further 3,600 because there are 3,600 seconds in a degree. In every minute, every degree is split up into 60 minutes and 60 degrees. So this is actually 1 arc second in radians. Fine, moving on then just to the actual formula part. It's this one over here. Here we are over here, the astrophysics section. And it's very important that you know all of these. This is Stefan Boltzmann's law. This one. This is Stefan Boltzmann's law. From that you can work out the luminosity of a black body. This relates to black body radiation. And this L is your luminosity. This is Stefan Boltzmann's constant, which you can get, which I discussed before from the constants. This is the surface area of the black body, and with the star we would work out that by 4 pi r squared, the radius. That gives the surface area of a sphere, and T is the temperature. That's your temperature in Kelvin. So from this we can work out the luminosity of the star if we know the temperature. If we know the luminosity and the temperature, we can work out the area, the surface area of the star, and from that we can work out the radius. We can work backwards. This over here is Wien's law. I think it's spelled like this. That's just 1 E I NS law. This is also for black body radiation, and this is where the maximum wavelength, or the wavelength where the maximum amount of energy is transmitted, gives the indication of the temperature of the object. And we usually have a graph something like this, where you have your intensity and we have a sort of a curve like this, where this over here, sorry about the diagram, is your maximum, this is your wavelength over here. So this wavelength over here is where the maximum amount of energy, the maximum intensity of light. And from that, if we know that, we can work out the temperature, because the temperature will equal 2.9 times 10 to the negative 3 divided by that lambda max. If we know the temperature, we can put it into this formula over here, and if we know the luminosity, as I said, we can work out the area, the surface area of the star. Let me just erase some of this because we need a bit of space here. Now this law over here, this is the parallax when stars shift by a certain amount in the sky as the Earth revolves around the Sun, and that shifting is given in arc seconds, the angle arc seconds, which, as I mentioned before, is 1/3600th of a degree in radians. Now when there's a 1 arc second shift in the star as the Earth goes around half a revolution around the Sun, then it was defined that this distance would be a parsec. So this automatically, when this is in arc seconds, then it gives our answer in parsecs. In the following formula here, we have our apparent brightness, which is the power per unit area per square meter that falls on the Earth or on some place from a star or the Sun, and it's dependent on, it's proportional to the luminosity of that object, and this d is the distance that it will be away. So for instance, the apparent brightness on the Earth is equal to the luminosity of the Sun divided by 4 pi d squared, where d is the distance from the Sun to the Earth, basically. And in here we have our following formula here. Looks a little bit complicated, but not too complicated. This m is the apparent magnitude, and this is the, as we have discussed, the scale, where 1 is your brightest star that can be seen with the naked eye, and 6 is the dimmest star that can be seen with the naked eye. And basically there is a 2.5 increase in the brightness as we go from a type 2 star to a type 1 star, or so forth, and this can extend. As we go down, we're actually getting brighter. So this is, each time we're going down, we're going 2.5 times, 2.5 times brighter, and so forth. Now this m over here is what we call the absolute magnitude, and this is the apparent magnitude if the star is 10 parsecs away from the Earth. This m is the apparent magnitude, is an indication or a measure of how bright a star is, and we can relate these two together, the apparent magnitude and the absolute magnitude, by this formula where the d is the distance that the star is away in parsecs. This is measured in parsecs. So for the standard level section, that concludes. With the high level section, this is looking at the relationship between the luminosity and the mass of the star, and it's of a factor of somewhere between 3 and 4. So when we get a mass that is bigger than the Sun, it gives there's a factor 3 to 4 times greater. This is looking at the Doppler effect, where this is delta lambda is the shift, as I've discussed in one of the videos, the shift in the wavelength due to the Doppler effect. And this is the actual wavelength, and this is gives us the recessional speed, how fast that galaxy or star is moving away from the Earth, and this is the speed of light. And we can put this into our V. This is Hubble's constant, H0, which is about 70. It's got quite I'll discuss that in more detail in another video. And this works. You can actually work out the distance that we are away. So that's Hubble's law. I'll discuss that more in a later video. All right. Thank you very much.